Hi everyone. So I need to carry on now with the second part of the paper one revision. So I did part one, which has gone over the energy and a little bit of electricity. So I'm going to try and finish off now and just mop all that up. Right, so let's crack on. Remember, if there's a bit that you know that you know, just sort of fast forward and then go on to the next bit. Any practical stuff, I'm going to do a separate practical stuff at the end. So just wait on for that one, please, guys. All right, here we go. We finished off last time, just ending with the types of components that we can have in a circuit. We talked about an LDR and a thermistor. What I want to talk about now is I want to talk about, first of all, about resistors generally. Okay, so resistors, if we're going to draw them, they look like this, don't they? And they can go in series like this, or they can go in parallel like this in a circuit. Now, if these are, say, 20 ohms each, okay, 20 ohms each, this one is going to have more resistance than this one is, even though they've got the same amount of resistance in each resistor, and that's because of the combination. So when they're in series, what we have to do is we have to add them together. So the total resistance, which we say RT, is equal to 40 ohms here. Okay, so if we've got resistors in series, we just add them together. But remember, if they are in parallel, we've got 1 over resistance total equals 1 over resistor 1 plus 1 over resistor 2. So this would be 1 over 20 plus 1 over 20. And then you just add them together. But remember, and it's the final step that people forget, that will then be equal to, so 0.2, 0.2, 0.4. That's going to be equal to, but you want RT, okay? So you're going to have to rearrange again in order to find RT. So remember that last little step there to get the resistance total, because some people just forget it and think that it's going to be 0.4 and it's not. So take care with that. Now, one of the questions that came at once was why, so what happens to the resistance when they're in parallel? The resistance goes down. So if I put them in series and then put them in parallel, the resistance is going to go down. And the reason for that, everyone, is because there's more pathways for the current to take. There's ultimately more wire. Okay, so you would say there's more pathways or routes or wire for the current to travel down. So that means the resistance actually reduces. So here the resistance would be a lot less than 40 than it would be the 40 ohms when they're in series. Okay. I don't know. What would I want to do next? No, I won't talk about practicals. We'll do that later. Done that one. Okay, the next bit is sort of mains electricity. Okay, mains electricity is things like the plug, which is really easy, about the wires in the plug. You know, the green and yellow and the blue and the brown wires. And remember, the brown is live, the blue is neutral, and the green and yellow is earth. Okay. Sometimes you might have to talk about the voltages on each of these as well. On the earth wire, it's at 0 volts unless something travels down it. Remember, it's just a safety precaution. The blue wire is basically it's connected to, it's like in a circuit basically. So it's going into the device through the brown wire and then coming back out through the blue wire down back to the power plant if you want. But then the live wire has a voltage of 230 volts. But the potential difference from the brown to the blue is actually going to be 230 volts as well. It's going from 0 to 230 volts is the difference between them. So make sure you know your wires in your plug. What else have we got? We've got wires in the plug. We've got the 230 volts, which is what goes into your home from the power station, and that is also at 50 hertz. That's the frequency which it comes in. Sorry guys, I've got a bad throat today. Right, I think let me have a look. Neutral. Yeah, actually, I think I'm going to make a prediction on this, guys, that this actually is going to be a bit more prominent in this year, talking about the wires. And that's what I was going to say before. The neutral wire as well, guys, sorry, is 0 volts. But of course, if it the difference between these two would be 230, but it's 0 volts on that one. Yeah, and remember, you can't forget those numbers. I'm still getting people getting these two wrong, 230 and 50 hertz. So make sure you know those two. That's what comes in through the power supply in a UK home. Oh yeah, let's talk about a fuse a moment as well. What's the purpose of a fuse? You put a fuse in the circuit as a safety feature. The current travels through here. If the current gets too high, if we're increasing the current and the current gets too high, then what happens is that this melts. Okay, the inside of the fuse melts. So therefore it's going to disconnect the circuit and the current won't flow. A little bit of a negative in this one is that, can't change my colours down here. Oh, there we go. A little bit of a negative in here is when it does melt in the middle there, it will take a few moments to melt. So in the meantime, you've actually already been electrocuted. So another type of safety feature used in a home is a circuit breaker. Okay, and circuit breakers are if the current coming into the home or the current, so imagine you've got like a dodgy toaster and it's calling for too much current, or the current rushes through for some reason, the circuit breaker will detect that and cut the whole thing off. So a circuit breaker is much better at keeping you safe. But both of those are two different safety features. You've all experienced it yourself, haven't you, in your homes where all the lights go out or all the electricity goes out on one floor, and that's the circuit breaker that's done that. And you just flick the fuse back on, and then it comes on. What else have we got here? Okay, this equation here, I reckon this is going to be quite prominent. E equals QV. If I rearrange that, V equals E over Q. This is actually a definition for voltage or potential difference. This is voltage here, this is energy, and this is charge. We measure voltage in volts, yeah? Okay, but actually, energy is measured in joules and charge is measured in coulombs. So another way to write a volt, guys, is joules per coulomb as well. So there's two ways in which we can express a volt. So how would I say what voltage is? It's the amount of energy per unit charge, the amount of energy per unit charge. So I want you to imagine if I have a circuit like this, and here's my cell, and here's my lamp, okay? Imagine we've got energy here, okay, at the battery where, or the cell where it's picking up the energy to go on with. And imagine here, I have a little bucket full of charge, okay? So here's my bucket full of charge. Here's my little electrons, okay? This is a coulomb that I have here. Okay, my little bucket full of charge. And what happens is, as they go by, they pick up a little bit of energy on their way through. Okay, and look, this is a volt. So it's basically how much energy per unit charge. So how much energy is it picked up? And then it takes that round to the lamp and drops it off at the lamp, that energy. And then there's work done here at the lamp. And remember, work done is force times distance. And that's basically the friction that's caused. Imagine if it was a normal light bulb, an old style light bulb like this, okay? You have a filament like that, okay? And then as the electrons rush through the filament lamp, they cause friction, and that friction is work done. So there's a force over a distance, work is done, and energy is transferred. Okay, so that's E equals QV. Just, it's one of those where people don't really remember that equation, but you've just got to try and, well, you know the score, don't you? If it gives you energy, if it gives you charge, and you're working out voltage, that's the one you're going to use. What else? What else? What else? We have our power equations as well, but again, it comes down to the same thing here, guys, that just find the right number, find the right equation, plug them into the right place. Let's go back to the top where we wrote down our equations before. Oh. Can't find them now. There we go. You've got these power equations as well here, haven't you? But it always just comes down to, you know, well, I've got current, I've got resistance, I've got to square the current, and then I've got the power times, you know, times by the resistance to get the power. Just put the numbers into the right place. Okay, what else? What else? What else? Static electricity. Let's have a look at that. So static. Common error here is that people talk about other things other than the electrons moving. So if I have, I don't know, a plastic rod, okay, imagine it's made of acetate, and imagine I have a cloth. Now the cloth, the stage that people miss out here, guys, is that they forget to talk about when it's neutral. So to begin with, before anything's happened, there's electrons on here, and there's obviously the protons that are fixed in position. Now, the only thing that can move here, guys, are the electrons. The electrons can move position, can't they? So a friction causes a separation of charge, and it can cause charge to build up in one area, for example. Now, we can have the scenario where if you have a cloth like this, sometimes you can get charge on one side and then none on the other. So you might get a build of electrons on one side and not on the other. So they all sort of travel to one side, or here you might have the usual amount, but here you've got more. Where you've got a balance between your positives and your negatives, guys, this is neutral. And we mustn't forget this stage, okay, that this can happen as well. But when you get a buildup of charge, which is an imbalance of charge, then this is where you have static electricity building up, okay? So imagine I rub this rod and all the electrons leave here and they go to the cloth. Okay, remember there's always the positives. They're all there already. And these electrons have left. Now, you must say that the cloth has become negatively charged. Little key here, guys. Just automatically call electrons negative electrons. Can't write today, sorry guys. Negative electrons, call them negative electrons, because then you're not going to miss out on any marks, because if you just say electrons and then don't explain that this is negative, you're not going to get marked. So from now on in, whenever you say electrons, just call them negative electrons, and then that's a mark in the bag there. Okay, you don't even need to say anymore. So yeah, the electrons will move. We might even end up with a situation where, you know, the electrons have all gathered on one end, like I'd said before. Okay. And so this end becomes positive and this end becomes negative. So there's a few different, you know, scenarios that can happen. You've got to just try and describe where the electrons have gone to, what charge, but what's been left on the other side. Is there anything over there? Is that positive now? Is that negative now? Yeah, but it's friction that causes the separation of charge, which then causes it to build up in one area. So there's lots of different types of things you can answer on static questions. Practice some static questions. Remember, it's a non-contact force, static electricity. Insulators and conductors is what I was going to say as well. If it holds onto the charge, like in this area here, it must be an insulator. Okay. If it lets the charge travel through it, then it's a good conductor. Did I mention thermal conductor? I did at the beginning of the other video, didn't I? Yeah. Thermal conductivity. So yeah, this is a really good insulator. It will hold onto the charge. And if I was all charged up and, you know, all my hair was all standing on end and every strand had a negative charge, all repelling each other, and then I touched something metal, then I'll probably get a bit of a static shock, won't I? Because the electrical charge will jump from me to the metal because it wants to travel through it really quickly, and it will discharge. And that's a really good word, that, guys. It will discharge the electrons away from my body. So if I wanted to discharge this here, I'd need some sort of earthing cable or something. Remember the word earthing as well? You know, something that touches it and lets the charge travel away really quickly. Remember, buildings, they have earthing cables that run through, like the Burj Khalifa has an earthing cable that runs right through the center, and it takes any electrical charge that comes from electrical storm all the way to the ground and earths it, so the electrical charge will spread out. You know what I didn't talk about a second ago was the national grid. Let's just have a quick look at the national grid for a second as well. National grid. Okay, so remember, you've got some sort of energy going into the national grid. This could be a nuclear power plant. This could be a coal-powered power plant, but either way, the systems work similarly. So you'll have, so I imagine this is coal, and it goes into a furnace here, and it burns, and then that's going to heat up some water that turns into steam, okay, and then that's going to turn a turbine, and that turbine is going to spin inside of a huge magnet. You know about this now because of electromagnetism, don't you? This generator here, what it's doing is because the wire is spinning inside of this magnet. Okay, so we've got a magnetic field that goes from north to south like this, and it spins inside of here. And because there's electrons in here, they will be affected by this magnetic field and they will start to move. So what happens is we generate electricity, and that goes into this, which is a transformer. Okay, so out of the generator, we then go into a step up transformer. Okay, and what that does is it increases the voltage and it decreases the current. So on a step up transformer, this is the primary coil and this is the secondary coil. We will have less turns on the primary coil and we will have more turns on the secondary coil. These are not connected to one another, these coils. There is just an iron core that runs through the center of both of them that's connected, but these create their own magnetic fields. So there's a magnetic field that's created around this because the electrons are traveling through, and then that induces another magnetic field around here and starts to make these electrons move. So remember, there's just wire sat here. These electrons are moving on this side, and it creates a magnetic field, and then it makes these electrons move on this side. But look, we've got more wire now, which means we're going to end up with a higher voltage on this side and a lower current. So that wire then goes up through the national grid. This is a terrible drawing of the national grid. Okay, which are the big pylons. The national grid is made of a system of transformers, wires, and pylons, and they take the electrical energy around the country. So then before it gets to our home, it goes through a step down transformer. And what that does is it reduces the voltage and increases the current. Now, on a step down transformer, on the primary coil, we have more turns. And then on the secondary coil, we had less turns. And of course, you have your transformer equation to use here as well, which we will talk more about when we get to paper 2, because actually I don't think you have your transformer equation in paper 1. Let me just double check. Yeah, you don't actually have to calculate anything at paper 1, but you do have to know what your transformers do. Okay, so step up, step down transformer, and then it goes into your home. And remember, when it goes into your home, it has 230 volts and 50 hertz. Okay, now when it leaves the power station, first of all, it has 23,000 volts. Then it's stepped up to 400,000 volts. And then it's stepped down again to 230 to make it safe. It goes into your home. Remember though, guys, it is current that actually kills you in an electric shock, not the voltage. But still, 400,000 volts, I'm sure, would do a lot of damage. So yeah, you need to make sure that you reduce that down. But yeah, the current actually is still fairly high when it comes into your home, so hence why it can still cause you an electric shock. Now, in this whole system, power equals current times by voltage. But can you see here, I'm increasing the voltage and decreasing the current up here. So actually, the whole time, the power stays the same. Okay, and then again, anywhere I measure it, the power here, the power here, the power here will be the same. And this enables us to be more efficient, which means we don't waste as much energy. So if I was to take the wire, here's the wire as it runs through the, you know, and this is on my my national grid. So I'm talking about this wire here. Okay, and I blow it up a little bit so you can see on the inside. There's, of course, there's atoms inside of there, or there's ions in the way. Okay, remember, most of you should remember this. It's called an ion lattice. Ion lattice. Oh my goodness, I can't function today. Ion lattice. Okay, and what happens is the electrons themselves, they try and get down this wire, and they will collide with the inside of the wire. If I have more current, it means I've got more electrons trying to do this all at the same time, and that's a bad thing. We don't want that to happen. So this is why we want the current to be low. We want a reduced current, because otherwise what's going to happen is we're going to get an increase in collisions. Okay, we're going to get an increase in unwanted energy transformations. Okay, and those energy transformations that I'm talking about are kinetic energy to, when they collide, will end up with thermal. Okay, so we're saying kinetic energy to thermal. We don't want that to happen. We want them to keep their kinetic energy. So this would then, if we have an increase in collisions, unwanted energy transformations, means that we would reduce the efficiency. Okay, which means there's more work done. Okay, so what do? We reduce the current so that we have less collisions. Okay, so that we have less unwanted energy transformations, so that we have an increase in efficiency. Okay, and we want less work done. And that will happen, guys, if we keep the current low as it travels through the wire. Okay, so that really is the national grid there. So you can relate power to those as well. Okay, the next thing is electric fields. Okay, if I have a charged particle, remember we were talking about static before. Imagine if I have an electron and it's negatively charged, and then I have a something that's positively charged, like a proton. There is a field that is created, like an invisible field around this that goes like this. Okay, and even though we can't see this because it's a non-contact force as well, it's like this invisible force that we can't see. These field lines, remember, this one's negative over here, and this one's positive. Okay. Try and get rid of this. Hang on. How do I get rid of this? There we go. We always have to draw these field lines in the direction in which a positive charge would flow. Okay, so imagine if I put a little positive charge here and I put a little positive charge here, which way would they flow? So in this case, positive and negative would attract, so it would go towards. Okay, so that's the direction in which the field would go there. Whereas here it would repel, so they are going to go outwards there. Okay, where would it be strongest, this field? It's going to be closer in. So the closer it is, it's going to be strongest. And the further out it gets, it's going to be weaker. So here it's strong and here it's weak. Okay, so that's electric fields. But in terms of a definition, it is the area around a charged object in which a charge will feel a force. Okay, so here's my positive charge. You're basically describing this, aren't you? It's the area around a charged object in which a charge will experience a force. Okay, so that's our definition for electric field. Area around a charged object in which a charge, or you could say a positive test charge even would be better. A positive test charge experiences a force. Okay, I think that's going to be in there, actually. I think there's going to be something about electric fields in there. Okay. All right, now what I'm going to do is I'm going to try and do a little bit of particle model of matter. Particle model of matter. Okay, first thing is solids, liquids, and gases. You need to be able to describe them properly. So a solid, liquid, gas. This is easy, right? But actually describing them is very finicky. You need to make sure you use the right language. So a solid, a liquid, and a gas. Okay. You're going to say here, they vibrate about a fixed position. Okay. These vibrate still, but they move freely. Okay, but remember, they're still touching. Okay, so they're moving freely, but they're still touching. Here, they basically take up the space. Which one's vibrating more as well? This one. Okay, so this one's got the most kinetic energy. All right, so it's going down in terms of increasing kinetic energy. Okay, what else have we got to describe? We've got to talk about, so we've talked about their position, then we've got to talk about their bonds between them maybe. So we might say here, the forces of attraction between the solid are large compared to a liquid. Okay, so they're large. The force of attraction between the particles are big. And then on a gas, the forces of attraction are a lot less. Or in fact, you'd say there aren't any forces of attraction, even though there are actually. Well, on a mark scheme, it said that there wasn't. What else have we got to say? Head's gone blank. Let's have a look. Let me see if I can get a diagram up. Solids, liquids, and gases description. Here we go. Look. This diagram here. Okay, so solid, the molecules that make up a solid are arranged in a regular repeating pattern, or you'd say vibrate in a fixed arrangement. They are held firmly in place, but can vibrate within a limited area. Can it be compressed? No, so the solids can't be compressed. Liquid molecules that make up the liquid flow easily around one another. They can be kept from flying apart by attractive forces between them. So there are some forces of attraction. The forces of attraction in these ones are more. Liquids assume this, so they take the shape of the container as well, don't they? And then we've got the molecules that make up a gas, fly in all directions, great speeds. They are so far apart that the attractive forces between them is insignificant. So basically there isn't any force of attraction between them. Okay, so make sure that you are as thorough as you can when describing those and practice doing those. Even though you think it's easy, just practice making sure you're describing your solids, liquids, and gases properly. Okay, next one. Okay, density is easy. All right, we're not going to go through any density at the moment. Let's talk about now specific heat capacity and specific latent heat. So specific heat capacity equation is change in energy equals mass times specific heat capacity times change in temperature, and specific latent heat is change in energy equals mass times latent heat. If I rearrange both of those to make latent heat and heat capacity the focus, specific heat capacity equals the change in energy divided by the mass times the change in temperature, and latent heat is equal to the change in energy over the mass. So let's have a look at our definitions now, and we can do this from our equations, can't we? So the specific heat capacity is the amount of energy required to change 1 kilogram of mass by 1 degree. Okay, because remember, this is change in temperature here that we have, isn't it? So this is measured in degrees Celsius. And then we've got latent heat is the amount of energy required to change 1 kilogram of mass to make it change state. Okay, so I'm not going to write out the full definitions here now, but because it take too long, but we've got the amount of energy required. This is specific heat capacity to change 1 kilogram of mass by 1 degree Celsius. And then we've got the latent heat, which is the amount of energy required. Remember, this little triangle here means change in energy. Okay, means changing the amount of energy required to make 1 kilogram of mass change state. So what do we mean by that? If I do a graph here of temperature and time, okay, and I put a line on here. Imagine I have an ice cube and I start heating it up. So this is a heating graph, and I start off with ice, and then so what's going to happen here is that it's melting. Okay, and then what's going to happen here is that it's evaporating. So it's melting, it's a liquid here, and then once it heats up even more, it evaporates and it turns into a gas. But what's happening? I start off with my ice cube that looks like this. Okay. And there's potential energy between the particles. Okay, let's just draw a few of them on like this. Okay, so these little squiggles here are supposed to be the potential energy. And actually, I write potential energy EP. I don't need to do it the wrong way around then. And then around the outside, we're going to draw these little vibration marks. Okay, and these little vibration marks are the kinetic energy that they have. So that's what they're moving. If I increase the temperature, what's going to happen is I'm increasing the kinetic energy. Okay, now this here is a solid, and everything has its own internal energy. It's basically, if it has temperature, it has kinetic energy, but it also, if it's held together in bonds like that in such a way, in fact, all atoms have potential energy, but there's potential energy, there's more potential energy when it's tightly packed like this, and if you and it needs energy to break it down. So potential energy is made up of internal energy is made up of potential energy and kinetic energy together. Okay, so here this ice cube has all that energy stored within it, and it's potential energy and kinetic energy as well. So when I'm heating it up, what's happening is that my energy is going into increasing the kinetic energy. So the kinetic energy starts to vibrate more. So here, as I'm increasing the temperature, this is increasing the kinetic energy. So every time we see here this on the slope, I've got an increase in kinetic energy. Where we see a flat part of the graph, this here is when we're having the energy go into the potential energy store. So this is the potential energy store, okay, where we're actually using the energy to break down these bonds that we have between these, and it's breaking that apart. So here, when I'm putting in, as I'm heating it up, remember, I'm putting in energy into this system. I'm increasing the temperature up the side here. So imagine I'm melting my ice cube. The energy that comes from the flame will be going into increasing the temperature out here, but here where it goes flat, the temperature stops increasing and the potential energy starts increasing, because, well, or rather, it's not increasing the potential energy, but rather it's starting to break it down, so it's going into that potential energy store. And then we've got more kinetic energy, and then we've got more. So here, guys, actually, I can label these different parts of my graph as specific heat capacity and specific latent heat as well. Specific heat capacity is when the temperature is increasing. Why? Because it's the amount of energy required to increase 1 kilogram of mass by 1 degree. So if I have an increase in temperature, it's specific heat capacity. When I have a change of state happening, which is here, this is specific latent heat. Okay, so wherever you see a flat part of the graph, this is specific latent heat. Wherever you see an increase in the graph, this is specific heat capacity. Okay, but internal energy is made up of two things: potential energy and kinetic energy. Okay. Right, what else do I want to say? Okay, what do I need to do? Give us a second. Oh, there's something about the specific heat capacity practical as well, but I'll do that in the other practical when we talk about insulation and stuff. So I won't talk about that right now. Oh, that's what I wanted to say. We have specific heat capacity, specific latent heat of fusion. So we've got specific latent heat of fusion here. And then we've got specific latent heat of evaporation. Oh, sorry, of vaporization up here. Vaporization up there. Okay, so remember, there's two different types of specific latent heat. There's fusion, where it's melting, and there's vaporization, which is where it's evaporating. Okay, just going to pause for a second, guys, just a second. Sorry, guys, Mr. Rogers came in. Okay, all right, next then. I want to think of an example. Yeah, this is what I wanted to do. This was in a paper a while ago, and I think they could repeat it, actually, thinking about it. I think this could be a good question. If you end up with an ice cube in your question and it asks you to work out It could work out any part of it. But whilst I'm melting the ice, hang on, let me think about the question here. Whilst I'm melting the ice cube, okay, there's energy going in at the bottom here. So imagine I've got my flame at the bottom here, which is my heat going in, okay? I'm putting in all this energy here, okay? But that's going into doing two things. It's going in to make it change state, but it's also going in to make it increase in temperature. All right. So what you might have to do is you might have to say, well, this total amount of energy here, this change in energy is going to be equal to the mass times by specific heat capacity times by the change in temperature. That's the specific heat capacity, because that's this bit. And I'm going to add it to M times L, which is, so this bit here is specific heat capacity, and this bit here is specific latent heat. But both of those are the amount of energy that's gone in to make it change state, because you had an increase in temperature and you had a change in state. So both of those things are equal to the total energy that went in. That's a really common thing that they do, actually, guys, is you've got to realize that if it's changing state and it's increasing in temperature, it's both of those things combined in the energy. So you might have to formulate something to do with that. Okay, right. Pressure. Oh, guys, these questions. You've got to be so specific about writing a pressure question, haven't you? You've got to make sure that you're using the right terminology. I always use this example because it just covers all bases. But imagine I have a balloon. Okay. And imagine I've got particles inside the balloon. Now, imagine I increase the temperature. I'm going to increase the kinetic energy of these particles. They are going to be vibrating more. So I'm going to increase the kinetic energy, which is going to increase the number of collisions. But here's where we've got to be specific. I'm going to increase the number of collisions between the particles and the inside of the container. Okay, so first of all, we've got to say the inside of the container. Okay, where is it colliding with? By the way, these always hit perpendicular, perpendicular to the surface. Okay, so just imagine them coming in at 90 degrees to the surface like this. Okay. Then if I have an increase in collisions, I'm going to have an increase in force, but I can't just say force. I feel like I've missed something. Increased collisions, but here, remember, I must say the rate of. Okay, so increase rate of, or you might say the number of collisions per second. So rate of or number of collisions per second. You don't get the mark unless you say those things. So let me just highlight this. Number of collisions per second, but also the inside of the container, okay, between the particles and the inside of the container. Got to say those as well. And then on this one, I get an increase in force because of the amount of collisions per unit area. Okay, got to say that bit as well there, guys, per unit area. Because you'd think you'd answer the question quite well if you just put these things, okay, temperature, kinetic energy, increase in collisions, increase in force, but you've got to say these things as well, otherwise I'm not going to give you a mark. So if I have an increase in force, then I have an increase in pressure, because pressure equals force divided by area. But remember, if I have an increase in force and it causes an increase in pressure, well, that's only going to cause an increase in pressure if the area stays the same. Okay, so you've got to say that bit as well. So really, it's a bit of a nightmare answering pressure questions, isn't there? There's so many things you've got to make sure that you include in order to get the mark. And you'll think you've answered it really well, but actually you won't get the mark unless you say all these bits in yellow as well. So remember, yeah, all right, I get an increase in force, which means I get an increase in pressure, because if force increases, pressure increases. But that's only the case if the area stays the same, because if the area actually increases as well, then that means that the pressure won't increase. Okay, so you've got to be very specific when answering a pressure question. Right, okay, that's everything on there. Oh, doing work on a gas, guys. This is a prediction I believe is going to be in there. Okay, so work. Oh, that's not what. It's not what I want. Work on a gas. Work done is force times distance. Imagine I had a pump, okay, like this, and that pump was going to a tire. I have to put in my chemical energy here in order to push this down. And then what happens is that energy goes into forcing the electrons here. Electrons, blimey, I'm still on electricity. What's wrong with me? Forcing the air particles down this tube. Now, that's great because my kinetic energy, or chemical energy, excuse me, has been converted into kinetic energy of the particles here and they've started to move. But then, because there is going to be friction happening here between the tube and the air particles, it means we're going to get some work done because each particle is going to apply a force over a distance, which means we're going to end up getting unwanted energy transformations. Okay, here, so friction, we end up losing some of that kinetic energy. So this is what work done on a gas is. So if you force a gas through an area, it's going to cause friction as it passes through, and then we're going to lose some of that kinetic energy and some of the overall energy that you're putting in. So this is why it's hard to like pump the air into the tire and you get tired because it's not actually that efficient because you're losing some. And again, when they get in there, they're going to be colliding with one another. There's going to be work done because of the friction on the surface of the inside of the tire, etc. So that's work done on a gas. There's a really good video on that on free science lessons as well, guys. Okay. What else have we got here? All right, that is it really, in terms of, you also have your formula as well, actually, excuse me, to do with pressure. Let's just talk about this for a second. So you've got your pressure formula where we're saying pressure times by volt. Now this is volume, this V, okay, not potential difference, not voltage. Pressure times volume equals constant. Now, what do I mean by that? What I mean is pressure 1 times by volume 1 equals pressure 2 times by volume 2. So if I have a pressure, imagine it's before. So I've got a pressure before and a pressure after. So pressure before, pressure, oh gosh, something wrong with me today, guys. Pressure before and a pressure after. And it could be any scenario where you've got, I don't know, pressurized container, and then we change the volume of the container, or we change the pressure inside there by forcing more particles in, or something like that. Okay. A range of different scenarios could come up, but I'm just going to put some numbers to this. So imagine my pressure to begin with is 10 and my volume is 2. Okay, so 10 times 2 is 20. Well, it means that everything on this side is going to equal 20 as well. But probably what's going to happen is one's going to go up and one's going to go down. So here now my volume has changed to 10 and this changes to 2, for example. Okay, so look what's happened. My pressure has decreased, but my volume has increased, but it still equals 20. So that's what that means, PV equals constant. What you might have to do is they might have a missing value and you might have to figure out what it is. But that's all right maths, isn't it? Where you imagine this is missing, this number 10, and you have to figure out that it's 10. So you have to do this, 10 times 2 divided by 2 will equal 10. So nice, easy equation to use that for pressure. The other pressure equation, which I've already mentioned, guys, is force divided by area as well. I think that's all I want to talk about in this video for now, because it's quite long. I'm just going to finish up with radioactivity, atomic structure on the last video, and then that's you good to go for paper 1. All right, bye guys.